How did ancient humans survive being sick with no medicine at all? You feel it before you open your eyes. That heavy, slow drag in your limbs. The throat that feels like it's been scraped with gravel. The dull throb behind your temples that pulses with every heartbeat. You know exactly what this is. You've been here 100 times before. You reach for your phone, cancel your meetings, maybe order some soup, and if it gets bad enough, you walk into a clinic and someone hands you a prescription. Now strip all of that away. No clinic, no prescription, no soup delivery, no ibuprofen, no antibiotics, no thermometer to tell you how worried to be. No warm bed with clean sheets, no roof necessarily, and somewhere out there just past the tree line something very large is listening for sounds of weakness. This was the reality of being sick for most of human existence. Not as a thought experiment, not as a dramatic hypothetical. For somewhere between 2,000,000 and 3,000,000 years, every single human being who fell ill faced it with nothing we would recognize as medicine. And yet somehow the species survived. More than survived, thrived. Spread across every continent on Earth, raised children, built cultures, painted the walls of caves in southern France, and carved figurines from mammoth, ivory in the steppes of Siberia. So the question isn't just academic. How did they do it? The answer turns out to be stranger, more sophisticated, and in some ways more humbling than you might expect. Because the story of ancient illness isn't a story of helplessness. It's a story of a body and a social system that were both in their own ways far more capable than we tend to give them credit for. Let's start with the body itself, because your immune system is older than you are. Much older. The innate immune system, the first line of defense that kicks in within hours of infection, is not a modern invention. It's ancient. Evolutionary biologist Charles Janeway spent decades mapping the mechanisms by which your body detects the molecular signatures of pathogens, what researchers call pathogen-associated molecular patterns. And what his work revealed is that the basic architecture of immune defense has been conserved across hundreds of millions of years of evolution. The toll-like receptors that trigger your inflammatory response. When a bacterium invades your tissue, fruit flies have them. Sea urchins have them. The specific design has been refined, but the fundamental logic detect signal attack is as old as complex life itself. What does that mean for your ancient ancestors? It means their bodies were not naive. They had been shaped by millions of years of coevolution with pathogens. Every epidemic that swept through a population of early Homo sapiens, every bacterial infection, every parasitic invasion left survivors and survivors passed on. Whatever immune advantages had kept them alive. This isn't a comfortable or gentle process. It is in fact one of the most brutal selection mechanisms in nature. But the result over geological time is a body with a surprisingly robust capacity to manage illness on its own. Your fever, for instance, is not a malfunction. It is a weapon. When your core temperature rises even a degree or two above normal, it creates an environment that many pathogens find difficult to replicate in. It accelerates the movement of immune cells through your bloodstream. It triggers the production of proteins that interfere with viral reproduction. Physician Matthew Kluger at Scripps Research Institute conducted studies in the 1970s showing that lizards, animals that are cold-blooded and cannot generate their own heat, will behaviorally seek out warm environments when infected, often at the cost of food and water, because the elevated temperature improves their survival odds. The fever is not an accident. It is an evolved response. Your ancient ancestors ran fevers, felt miserable, and their bodies were doing exactly what they were designed to do. The same is true of the fatigue you feel when you're sick. That crushing heaviness, the inability to want to do anything except lie still, that is not weakness. That is your immune system demanding resources. Cytokines, the signaling proteins that coordinate your immune response, act directly on the brain to induce what researchers call sickness behavior, social withdrawal, reduced appetite, increased sleep, lowered motivation. This is not random. Sleep is when your immune system is most active. Your body is not failing you when it forces you to rest. It is prioritizing the battle happening inside you over every other possible activity. For a hunter-gatherer living in a band of 20 to 50 people, this had direct consequences. It meant stepping back from the daily tasks of foraging, hunting, and camp maintenance it meant depending on others. And here is where the story takes its first unexpected turn. Because the social structure of early humans was not just an emotional comfort during illness, it was a medical infrastructure. Anthropologist Kim Sterlny has written extensively about the way that early human groups functioned as what he calls apprenticeship networks densely, collaborative communities, where knowledge, resources, and care were shared in ways that had no real precedent in the animal kingdom. Archaeologist Nicholas Connard and his colleagues examining the Middle Stone Age sites at Blombos Cave on the southern coast of South Africa, a site occupied by anatomically modern humans at least 75000 years ago, found evidence not just of tool manufacture, but of the kind of sustained, complex behavior that implies stable social organization. People were living together, working together, planning together. And people who live together look after each other when they're sick. We have direct skeletal evidence of this. One of the most striking archaeological finds in the story of ancient care is the skeleton known as Shanidar, one found at Shanidar Cave in what is now Iraqi Kurdistan. Excavated by paleoanthropologist Ralph Selecki in the 1950s, this Neanderthal individual who lived roughly 45000 years ago had survived to what would have been a relatively old age, despite suffering from a withered arm, a fused knee, severe arthritis, and evidence suggesting he may have been partially blind in one eye. Several of these conditions were clearly present for most of his adult life. He could not have been a fully productive member of the group in terms of hunting or heavy labor. He was kept alive by the people around him. There is no other explanation. Now, researchers are careful, and rightly so, about over-interpreting any single skeleton. The interpretation of Shanidar I has been debated, but he is not alone. Across multiple sites and multiple hominin species, archaeologists have found individuals who survived serious debilitating injuries and illnesses for extended periods long enough for bones to heal, long enough for chronic conditions to develop, long enough that survival required external care. The pattern is consistent enough that most paleoanthropologists today accept that deliberate care of the sick and injured is genuinely ancient behavior. But what did that care actually look like? This is where the archaeological record becomes frustratingly silent, and where comparative anthropology becomes an essential tool. When researchers want to understand behaviors that leave no direct physical trace, they look at present-day hunter-gatherer societies as what scholars call analogs, not as unchanged windows into the Stone Age. The Hadza of Tanzania, the Jew, Hawansi of the Kalahari, and the Tiwi of Northern Australia are contemporary people living contemporary lives shaped by their own histories and circumstances. But in terms of how they respond to illness without access to biomedical care, they provide genuinely useful data. What those communities show is a consistent pattern of botanical knowledge that is far more sophisticated than casual observers expect. Ethnobotanist Paul Allen Cox spent years documenting the medicinal plant knowledge of traditional healers in Samoa and found that a remarkable proportion of the seed plants they used had measurable pharmacological activity, active compounds that in laboratory conditions showed anti-inflammatory, antimicrobial, or analgesic effects. This is not magic or coincidence. This is the product of tens of thousands of years of careful, cumulative experimentation, the kind of slow-motion clinical trial that operates across generations, where what works gets remembered and passed down, and what doesn't gets quietly forgotten. Your ancestors were doing the same thing. They were watching. They were testing. They were noticing that when an animal ate a particular plant, its behavior changed. They were observing that certain berries provoked vomiting, that certain bark seemed to reduce swelling, that certain roots, when chewed, dulled pain. This empirical tradition, empirical in the truest sense, based on observation and consequence rather than theory, is what eventually became pharmacology. The willow bark that Bayer chemists eventually synthesized into aspirin in 1897, people in multiple cultures had been chewing it for thousands of years before that. The active compound salicin had been doing its job in human bodies long before anyone understood why. Archaeologist Marta Mariotti Lippi and her colleagues published an analysis in 2015 of dental calculus, essentially fossilized plaque from Neanderthal teeth, found at El Cidrón Cave in Spain. What they found embedded in the mineralized material included poplar, which contains salicylic acid, the same compound as in willow, bark the precursor to aspirin, as well as traces of mold, related to penicillium, the genus from which penicillin was eventually derived. Whether the Neanderthal individual was intentionally consuming these for medicinal purposes or encountered them incidentally is genuinely unknown. But the presence is striking. The tools of relief were already there available and possibly being used. There is also strong evidence from multiple archaeological contexts that early humans understood something about the relationship between contaminated water, illness even without germ theory, to explain the mechanism. At many Paleolithic campsites, researchers find evidence of settlement near, but not directly at water sources, with waste disposal areas situated downstream and away from sleeping and food preparation zones. The understanding of contamination may have been entirely experiential, rather than theoretical. You notice that the people who drank from the place downstream, from where others relieved themselves, got sick more often, but the behavioral response was functionally the same. Now here is the counterintuitive twist. Because when you look at the skeletal record across the transition from hunter-gatherer life to agriculture, beginning roughly 10000 to 12000 years ago in the Fertile Crescent, and spreading from there, something ended at. Unexpected happens. Health gets worse. This is not a fringe claim. It is one of the most robustly documented findings in the entire field of paleoanthropology. Bioarchaeologist Clark Spencer Larson has spent decades analyzing skeletal collections from populations that lived through the agricultural transition, and the pattern he describes is remarkably consistent across geographic regions. Hunter-gatherer populations tend to show taller, average stature, fewer signs of nutritional deficiency, less evidence of infectious disease in their bones, and greater bone density than the early agricultural populations that followed them. The skeletal record of early farming communities is riddled with evidence of iron deficiency anemia, visible as a condition called porotic hyperostosis on the skull, as well as stunted growth, increased infant mortality, and the unmistakable signatures of epidemic disease. Why? Because agriculture changed the disease landscape in several simultaneous and catastrophic ways. Sedentary settlement meant that human waste accumulated near living areas instead of being left behind at each campsite. Stored grain attracted rodents. Domesticated animals, cattle, pigs, sheep, chickens, lived in close proximity to humans, creating the conditions for zoonotic transmission. The jumping of pathogens, from animal populations to human ones. Most of the great epidemic diseases of history, smallpox, measles, influenza, tuberculosis, have their origins in this transition period, when humans began living in close enough proximity to large enough populations of animals that cross-species infection became a regular event. Your Paleolithic ancestors were not disease-free. That would be an absurd claim, and the evidence doesn't support it. They dealt with parasites, with injuries, with respiratory infections, with foodborne illness. But they were protected from the great epidemic killers, the diseases that required dense sedentary populations to sustain themselves simply by the way they lived. Mobility was a form of epidemiological protection that they probably didn't know they had. So let's reconstruct what actually happened when a person in a mobile hunter-gatherer band fell ill around 30000 years ago. Not dramatically, just ordinarily. A stomach illness perhaps, a respiratory infection, something your body knows. You wake up feeling wrong. Immediately, the people around you notice, not because you announce it, but because in a group of 20 or 30 people who have lived together for years, a slight change in your movement, your color, your energy is visible. You're not expected to push through. That is not what happens. Someone brings you water. Someone stays close. The group's movement for that day, the territory they plan to cover looking for food, adjusts. If you are mobile enough to travel, you travel. If you are not, someone stays with you while others go. This is not sentimentality. This is a system. In a world where every person's knowledge and labor contributes to the group's survival, keeping group members alive when they are ill is a rational investment. If someone in the group has knowledge of plants, and in most hunter-gatherer societies documented by ethnographers, multiple adults hold significant botanical knowledge, not just designated specialists. They may bring you something. Bark to chew, leaves to press against a wound, something brewed in water over a fire, You rest. You drink water. Your body does most of the work. And most of the time it works. Because most infections that would have reached your ancient ancestors before the zoonotic explosion of the agricultural transition were infections the human immune system had been co-evolving with for a very long time. The outcome was not always survival. Child mortality was significant. Old people died of things we would now treat in an afternoon. But the population survived, grew, and spread, which means the system was functional. The part that gets me, and I'll be honest about this, is not how primitive the medicine was. It's how social it was. Every response to illness that the evidence points toward is deeply relational. It requires other people. It requires someone to notice that you're sick, someone to bring you water, someone to adjust the group's plans, someone to carry the knowledge of which plants might help. Illness was not a private crisis, managed between an individual and a healthcare system. It was a communal event responded to by a community. We have in many ways built extraordinary things since then. The germ theory of disease, antibiotics, vaccines, surgical technique, diagnostic imaging, these are genuine miracles, and framing them otherwise would be dishonest. The average human lifespan has more than doubled in the past 2 centuries, and that is not a trivial achievement. When your child runs a fever of 104, you should take them to a doctor. When you have a bacterial infection, you should take the antibiotics. But something was also present in those small bands of 3,000 years ago that we have in some ways lost. The visibility of illness, the expectation of mutual care, the understanding that a sick person's recovery is a communal concern, not a private one. In the modern world, illness has become largely invisible and largely privatized. You suffer alone or in small family units, largely cut off from the broader social web. The extended network of people who notice when you're struggling, who adjust their plans around your illness, who bring you something and stay close, that network has shrunk considerably. Your body still knows how to fight. It has been doing it for 3,000 years. The immune response, the fever, the fatigue, the aching need to be still, and rest. Those ancient mechanisms are running exactly as designed every time you get sick. You don't need to do anything special to activate them. They were there before you were born. What your body also knows at some level is that it was never meant to do this alone. The research on social support and immune function is remarkably consistent. People who are socially isolated tend to have measurably different immune responses than people embedded in strong social networks. Loneliness, it turns out, is physiologically stressful in ways that directly compromise the immune system. The neuroscientist John Cacioppo spent years documenting this connection, and what his work suggests is that your nervous system and your immune system evolved together in an environment where being alone was dangerous and being connected was protective. When you wake up sick tomorrow, and you will at some point, and you reach for your phone to cancel your meetings, take a moment. The ibuprofen you're about to take is a descendant of the willow, bark your ancestors chewed. The rest you feel compelled to take is the same sickness behavior your immune system has been enforcing for millions of years. The person who checks in on you, who brings you soup, who adjusts their day because you're unwell, they are participating in something older than civilization, something that for most of human history was not optional. It was the medicine. You wake up feeling wrong, and the oldest, most reliable treatment in human history is already running.